Okay, so this brings me to the first one that I think I'm a little excited to do, the exponent. Oh, no, actually, I'm not really sure I'm that excited about the exponential function, but I was looking forward to the Ackermann function because that has an interesting name. But let's do the exponential function first. So in this case, we want to implement a function that computes the exponential function using recursion. So we need to somehow use this relationship that x to the power of n is equal to x times x minus to the power of n minus 1 to compute it recursively. So how can we do that? Well, what recursion does is that it considers a base case, and then it considers a way of computing the other cases using a somehow simpler case. In this case, simpler is defined as n being closer to 0. So let's just try to implement this. I really like this kind of problem because it exemplifies a strategy that I have discussed before for implementing things in Python, namely where you start with the simplest case first and then you try to expand it. So we need to compute the exponential function f of x comma n, so it computes x to the power of n, and then we need to use this complicated equation somehow. But we can just notice that if n is equal to 0, it should return 1. And that's something that I think I can do. So let's start with that case, and we work in this function, this file here, and then let's move on to the other things we need to do. So let's do exponential. Yeah, there's a little bit of help. We don't need help. So what I'm going to do here is that I'm going to call my function exponential with an input argument of x. Let's say x is equal to 2. That's a nice number. And then n is equal to 0, just to be clear what the inputs are called. So x is equal to 2, n is equal to 0, x is equal to 2, n is equal to 0, and then we need to do something here. Well, in that case, n is equal to 0, we return 1. So what I can just do here is I can return 1. If n is equal to 0, return 1. And then I'm done with sort of the base case of the exponential function. Let's check that it works. Okay, so let's try to think about another case. Let's think about the case n is equal to 1. So if you think about, and we think about this relationship for n is equal to 1, what does it say? It says that n x raised to the power of 1 is equal to x times x raised to the power of n minus 1. And that's equal to x times x raised to the power of 0. X raised to the power of 0, and this is where we need to think about recursion. That's something that we can actually compute using this method that we already implemented, by just saying n is equal to 0. So when we use recursion to compute this example, what we really mean is that we use a function we already defined for a simpler n, and then we use some kind of mathematical relationship that gives rise to the recursion. In this case, it was this equation that I used. Let's think about a more general example. So let's say that n is equal to 2. In that case, it says the same thing here. And that means that it says x times x raised to the power of 2 minus 1. And that can be computed by saying by using this relationship. And then you can think that if I have a general n here, actually what happens, this will be superfluous. I get this general relationship. So let's think about how I can use it. So what I can do is that if n is greater than 0, I can use this relationship. So I'm just jumping over this case because I want to handle it last just for fun. N is equal to 0, n is less than 0, so this case must be n greater than 0. So if n is greater than 0, what do I return? I return the relationship I have here. So what I can just do is that I return x raised to the power of n, but that's equal to x times the exponential. So actually what I just need to return is this expression, because that is valid Python code. And now I should actually be able to compute an exponential function for n greater than 0. Okay, so how do you check? How do you start to check if you did this correctly? Obviously, you start with n equal to 1, because we know that 2 raised to the power of 1 is supposed to be 2. That's easy to do in our head. So we can check that we seem to have done this correctly. So let's try. It does give 2. So that's good. And then you can think about n equal to 2. 2 raised to the power of 2, that should be 4. 2 raised to the power of 3. And now it starts getting tricky, so let's not do that. Let's instead do 3 raised to the power of 2, just to confirm some other values. That should be 9. And it works. And it actually works for, let's do 10. This will be equal to 2 raised to the power of 10. And that's going to be equal to 1024. When you work a bit with programming, you really start to know your 2 raised to something table. So now this function works for n equal to 0, n greater than 0. But we want the general exponential function. We also want n less than 0. What can we do in that case? Let's say we have x raised to the power of n, and we need to do this. So how can we do that using a general function here that works when n is greater than 0? Well, what we can do actually is we can say that this is mathematically equal to 1 divided by, and now you need to remember your high school math, which can be, I know from experience, very tricky. I mean, I'm not saying that to be facetious, but I actually make an embarrassing amount of mistakes with stuff like that. But if you think a little bit about it, this relationship is actually true, right? Because let's think about an example. Let's think about an example. N is equal to -2, right? And then we have 3 raised to the power of -2, well, that's equal to 1 divided by 3 raised to the power of 2. And that's all this relationship is expressing. This is a general mathematical relationship, and it's actually the relationship that will be implemented here with our general function f, that stands for the exponential. So in other words, what does that mean? It means that the x raised to the power of n, when n is less than 0, is actually given by our exponential function of x, and then minus n, 1 divided by this. It's simply what I had up here. I have the 1 divided by the exponential function for the negative exponent. This is only true, this is only something that's useful, it's generally true, but it's only something that's useful for us when n is less than 0. So what I do here is that I check if n is less than 0. In that case, I just use this relationship that I have here. Exponential of x and minus n. Let's do an example. So it's a little hard to compute the inverse of numbers in our head. So maybe we can do it like this. So we can for instance do, let's say 3 raised to the power of -2. So what is that equal to? Well, in Python we can, I don't know, it does this mouse over thing, it's really annoying. It's equal to 1 divided by 9, right? 1 divided by 3 times 3. So let's just print that out. And what does our exponential function say? Sorry, go away. Go away. We get exponential of 3 and -2. And let's see if they're the same. They are. So I think this function is implemented correctly. So let's remove all the print statements just to clean up the output. This error is never going to be reached, so we can just remove it. Let's just sanitize it completely. And then run the exponential. And it seemed to work. So we did this correctly. Now just one last thing. Instead of doing this if, this way of doing it, there's like a greater chance, I'd say, that you forget a case. Like somehow there is a value of n that you don't catch. What you can do instead is actually you can say, if this is true, do this. Otherwise, else if this is true, do this, and else do this. This way you're guaranteed that one of these return statements will be hit. And when you say else, you of course don't include another statement, because this is the catch-all. If, do this, else, this is true, do this, else, do this. This would be another way of doing it. And it still works. Good. So that was that. Now I'm finally getting to the exercise that I was looking forward to. But that will be in the next video.